Imagine logging into your primary bank account tomorrow morning, right?
Yeah, just your normal routine.
Exactly. But when the page loads, the interface is completely bare. Like the login box is gone.
Wow, okay.
Yeah, there's no field for your username, no field for your password. I mean, there isn't even a forgot password link hidden in the footer.
I mean, for a traditional banking customer, that looks like a catastrophic system failure. It basically looks like the bank simply ceased to function.
Right. And if you were to, call up your branch in a panic, the manager would casually inform you that they no longer maintain a database of your account.
Like they just deleted you.
Yeah, in fact, they'd say they don't have a central server tracking who owns what at all. The entire concept of them, like, holding your identity has just been erased.
Which is terrifying for most people.
It is, and it brings up the fundamental question we're unpacking for you today. Like, how does a financial system exist in a total vacuum of central authority?
Right. How do you prove you own your money when there is no server to authenticate your credentials?
Exactly. So we are taking a deep dive into the absolute bedrock of this paradigm shift. Today, we are tearing down the cryptographic primitives that make every single blockchain functional.
The foundational stuff.
Yeah, we're looking at hash functions, public and private key pairs, digital signatures, and Merkle trees, and how all of that esoteric math eventually condenses into those seed phrases sitting in your hardware wallet right now.
It's a complete inversion of how we've handled digital trust for the last 40 years.
Oh, absolutely.
Like in the legacy internet, trust is entirely centralized. You trust the bank's database to not alter your balance, and they trust your password to grant you access.
It's a two-way street of centralized trust.
Exactly.
Yeah.
But in a decentralized network, math replaces the database entirely. The security guarantees aren't based on some company's internal policies. They're enforced by the laws of physics and computational complexity.
Right, the math literally won't let you cheat.
Yeah. So if you want to understand how crypto actually operates under the hood,
Mm-hmm.
beyond the market speculation,
Mm-hmm.
you really have to understand the byte level machinery that is replacing that trusted server.
I totally agree. And to shortcut your way to being, like, deeply well-informed here, we have to start with the most basic building block, which is data identification.
The fingerprint.
Right, the fingerprint. Because if we don't have a centralized database to index information, we need a way to look at a piece of data, whether it's a single text file or a massive compiled smart contract, and guarantee its identity without a shadow of a doubt.
Right.
And this is where cryptographic hash functions come in. So what exactly is happening there?
Well, a hash function is essentially a one-way mathematical meat grinder for data.
A meat grinder. I love that.
Yeah, it's the best way to visualize it. You can feed it an input of any size. I mean, it could be a single byte representing the letter A, or it could be a massive terabyte-sized video file.
Doesn't matter.
Doesn't matter at all. The algorithm processes that data and produces a fixed-size output, typically referred to as a digest or simply a hash.
Okay, but standard programming languages have basic hash functions built in for things like data sorting anyway, right?
They do, yeah. But when we talk about cryptographic hash functions in the context of blockchains, we are demanding a much, much more rigorous set of mathematical properties.
Let's break down those rigorous properties then, because I know the math here is pretty unforgiving.
Very unforgiving.
So the baseline requirement is that the function has to be deterministic.
Right.
Like if I run a specific PDF through a hash function on my machine today, and you run the exact same PDF through the same function on a totally different architecture, like 10 years from now, we have to get the exact same fixed length string.
We have to. The entire consensus mechanism of a blockchain relies on that deterministic property.
Because everyone has to agree on the state of the network.
Exactly. You have tens of thousands of nodes distributed globally, right? They're running on different hardware, different operating systems, all processing the exact same transactions.
Right.
If the hash function had even a microscopic variance based on, say, the local environment, nodes would compute different block hashes.
Oh, and then the chain would just splinter.
Yeah, the chain would fork infinitely, and consensus would be completely impossible. So determinism ensures that the fingerprint of the data is a universal constant.
Okay, that makes sense. So the second requirement is pre-image resistance.
Yes.
And this is the one-way nature of that meat grinder you mentioned earlier, right? It's computationally trivial to compute the hash if you have the input, but it is effectively impossible to derive the input if you only have the hash.
Exactly. And this is a crucial distinction that often, trips up developers moving into cryptography for the first time.
How so?
Well, hashing is fundamentally distinct from encryption
Right, because people use those terms interchangeably all the time.
all the time. But they shouldn't. Encryption implies a two-way mathematical operation. Like, a key exists to reverse the ciphertext back into plaintext.
But a hash has no key.
Exactly. A cryptographic hash has no key whatsoever.
Yeah.
The operation destroys the original structure of the data entirely. You can't put the hamburger back together to make a cow.
That's such a visceral image, but it works so well.
Yeah, the only theoretical way to reverse a hash is a brute force pre-image attack.
Which means just guessing every single possible input.
Right. Guessing every conceivable input, hashing it, and checking if the output matches your target hash.
Which is why hashing low-entropy data is a massive vulnerability, right? I mean, if you hash a 4-digit PN, an attacker doesn't need to break the mathematics of the hash function.
No, I don't.
They just run all 10,000 possible 4-digit combinations through the algorithm in, like, a fraction of a millisecond and just match the output.
Precisely. Pre-image resistance really assumes the input data has enough entropy, enough randomness to make brute forcing impossible.
Right.
And when utilized correctly, this property allows you to commit to a secret without actually revealing it.
Like a sealed bid auction on a blockchain.
Yes, perfect example. You want to submit your bid, locking it in so you can't change it later, but you don't want anyone else to see the amount until the bidding period ends.
So you just publish the hash of your bid?
Exactly. The network records your commitment. Then, when the reveal phase snooks, you publish the plaintext bid. Anyone can hash your revealed bid, compare it to your earlier commitment, and verify you haven't altered your number.
That's so clever. And that actually brings us to the avalanche effect, which kind of acts as the tamper evidence seal for the entire network.
Oh, the avalanche effect is my favorite part.
It's wild. The math requires that changing a single bit of the input, like just flipping one microscopic 0 to a 1, must scramble the output so completely that it appears entirely uncorrelated to the original hash.
Yeah, the technical term for this is a strict diffusion and confusion requirement.
Okay, let's give an example of that.
Sure. So if we take a simple text string, like the word hello in all lowercase,
Yeah.
in ASCII binary, that string has a very specific bit representation.
Right.
If we change it to help with a P, we've only altered 5 bits at the very end of the string.
Just a tiny, tiny fraction of the data.
Right. But if you run both through the SHA-256 algorithm, the hash of hello begins with 2CF24dB, while the hash of help begins with FTD7585E.
They don't share a single visual or mathematical similarity. Like, there is no gradient of closeness at all.
None. You cannot look at two output hashes and deduce that their inputs were structurally similar.
Wow.
And this avalanche effect is exactly what makes a blockchain immutable.
Right, because everything is linked.
Exactly. If a malicious actor tries to go back to a block mine, say, 3 years ago, and change a single transaction, like altering a transfer from 10 tokens to 100 tokens, the hash of that specific transaction changes completely.
And because that transaction hash is bundled into the block header, the entire block's hash changes completely.
Yes. Which immediately invalidates the subsequent block and every single block after it. The tamper is instantly mathematically obvious to every node on the network.
That is just brilliant. Okay, so the final vital property here is collision resistance.
Right.
Pre-image resistance means it's impossible to find the specific input for a given hash. But collision resistance means it's infeasible to find any two different inputs that produce the exact same output hash.
Yeah, because if you can reliably find collisions, the entire system fails.
Because you could just substitute a malicious piece of data for a legitimate one without anyone noticing.
Exactly, without alerting the network at all. Now, because a hash function compresses an infinite amount of potential data into a fixed size output, we know for a mathematical certainty that collisions must exist.
Right, the pigeonhole principle. If you have more pigeons than holes, 2 pigeons have to share a hole.
Precisely. But a robust cryptographic hash function makes finding those collisions computationally out of reach.
Well, let's quantify out of reach for a moment, because we're usually dealing with 256-bit outputs in blockchain architectures, right?
We are, yeah.
Like Bitcoin relies heavily on SHA-256, while Ethereum utilizes KEKAK-256. Both output a string of 256 ones and zeros. So the number of possible combinations is 2 to the 256 power. I feel like human brains are just uniquely unsuited to conceptualize a number that large.
Oh, it is a magnitude that completely defies human intuition. 2 to the 256 power is roughly 1.15 times 10 to the 77.
That's a lot of zeros.
It is. For context, the estimated number of atoms in the entire observable universe is roughly 10 to the 80th.
Wait, really? So it's almost the same scale?
It's very close. So finding a specific hash is akin to picking a single specific atom out of the universe.
That's insane.
So when cryptographers say brute forcing a 256-bit space is infeasible, they don't mean like we just need faster processors. They mean it is a physical impossibility given the thermodynamic limits of computation in our universe.
That is mind-ending. But, since we brought up SHA-256 and KEK-256, there is a really fascinating historical divergence here between Bitcoin and Ethereum.
Oh, absolutely.
Like, SHA-256 was developed by the NSA and standardized by NIST, and Satoshi Nakamoto used it extensively in Bitcoin, often hashing data twice, which is known as double SHA-256, to defend against potential length extension attacks.
Right. Very paranoid, but very secure.
But Ethereum went with KEK-256, and it created one of the most notorious development traps in the entire industry.
Ah, yes. The famous NIST padding foot gun.
Tell us about that.
So in 2012, KEK actually won the NIST competition to become the new SHA-3 standard.
Okay.
And Ethereum was in its early development phases at the time, and they eagerly adopted KEK to hash its state and transactions.
Makes sense. It was the shiny new standard.
Right. However, before NIST officially finalized the SHA-3 standard in 2015, they altered the padding scheme.
Uh-oh.
Yeah. The padding scheme is just the way data is padded out to fit the algorithm's block size before the math is applied.
Wait, so the algorithm that Ethereum integrated wasn't actually the final standardized SHA-3-256?
Exactly. Ethereum's KEK-256 opcode uses the original padding scheme submitted to the competition, which differs slightly from the official NIST SHA-3-2526 standard that everyone else uses.
Oh man, that is a trap.
It really is. So if a developer unknowingly uses a standard out-of-the-box SHA-3 library from a modern programming language to hash a message on their front end,
Right.
and then a smart contract tries to verify that hash using Ethereum's native KEK-256 opcode, the outputs will be completely different.
Because the padding is different.
Exactly. It's a subtle byte-level discrepancy that has caused literally countless hours of debugging for developers entering the Web3 space.
I can only imagine. Okay, so we now have an unforgeable fingerprint for our data. We can mathematically prove a transaction hasn't been altered. But on a public ledger, knowing the data is intact doesn't solve the core problem, which is authorization. Like, if anyone can broadcast a hash to the network, how do I prove that I authorize a specific transaction without broadcasting a password for the whole network to just steal?
Right, and this requires a major shift from symmetric cryptography to asymmetric cryptography.
Okay, break that down for us.
So, for decades, cryptographic systems were primarily symmetric, meaning you used a single shared secret key to both encrypt and decrypt data.
The fundamental flaw there being key distribution, right? Like, if I want you to read a secure message, I have to securely transmit the key to you. And if that channel is compromised, the encryption is totally useless.
Exactly. It's the classic spy problem. How do you share the codebook without the enemy intercepting it?
Right.
Public key cryptography, or asymmetric cryptography, solves the key distribution problem completely. Instead of one shared secret, a user generates a mathematically linked pair of keys. You have a private key, which is a truly random number that you generate locally on your own machine, and you never transmit to anyone, ever.
Got it.
And from that private key, you use a one-way mathematical function to derive a public key. Because the derivation is strictly one-way, you can broadcast your public key to the entire world without compromising your private key.
I think of it like this. The private key is your physical ability to sign an unforgeable signature, right? And the public key is just a published copy of that signature that anyone can check to verify it was you.
That's a really great analogy, yeah.
Now, the early internet relied heavily on the RSA algorithm for this, but blockchains almost exclusively use elliptic curve cryptography, or ECC. So why the shift? I mean, if both secure a network asymmetrically, what makes ECC the dominant primitive here?
It really comes down to efficiency and scale. RSA relies on the mathematical difficulty of factoring the product of two massive prime numbers.
Okay.
To maintain security against modern computing power, those RSA keys have had to grow incredibly large, typically 2048 or even 3072 bits.
Which takes up a lot of space.
Right. Elliptic curve cryptography relies on a completely different mathematical foundation, the elliptic curve discrete logarithm problem.
That's a mouthful.
It is. But because the math underlying ECC is vastly harder to break per bit than RSA factoring, a 256-bit ECC private key offers the exact same equivalent security as a massive 32-bit RSA key.
Oh, wow. Which is obviously paramount when you're designing a distributed ledger. Like, you want to minimize the byte size of every single transaction so that thousands of nodes can store and verify the chain without requiring, enterprise-grade hardware.
Precisely. You want people to be able to run nodes on Raspberry Pis.
Right.
So let's look at the mechanics of this curve. An elliptic curve is a set of points defined by an equation, typically something resembling y squared equals x cubed plus x plus b.
Okay. Taking me back to high school algebra.
Yeah, but we aren't graphing this on a standard Cartesian plane. The math is calculated over a finite field, meaning the coordinates are integers modulo a massive prime number.
So the math wraps around, like a clock face. If you
Yeah.
go past 12 on a clock, you loop back to 1.
Exactly. That's finite field arithmetic. This modular arithmetic bounds the numbers and keeps them within a specific bit size.
Okay.
Now, the cryptographic magic happens through an operation called point addition. The curve defines a geometric way to take 2 points, draw a line through them, find where it intersects the curve again, and reflect it across the x-axis to get a third point.
Sounds complicated.
Geometrically, it is a bit weird, but by repeatedly adding a point to itself, we perform scalar multiplication.
And this is how the key pair is generated, right?
Yes, the network protocol establishes a universally known starting point on the curve, which is called the generator point, or just G.
Okay. Everyone agrees on G.
Right.
Yeah.
Your private key is simply a massive random integer. Let's call it K. To find your public key, you take the generator point G, and you mathematically add it to itself many times. Your public key is the final coordinate on that curve.
And the asymmetry exists because while it is computationally trivial for my computer to multiply G by my private key K to find the public coordinate, an attacker looking at my public key coordinate cannot just divide it by G to figure out what K was.
Exactly. Division on an elliptic curve doesn't exist in the same way. The modular arithmetic of the finite field scrambles the path. It looks like chaotic jumping around the curve. They would have to calculate every single point addition one by one to find your key.
Which would take until the heat death of the universe.
Exactly. That one-way trapdoor is the elliptic curve discrete logarithm problem. It is the fortress wall protecting trillions of dollars of value right now.
Wow.
Now, the specific curve chosen dictates the exact parameters of the equation. And Satoshi Nakamoto selected a curve called Sec256K1.
Which at the time in 2009 was a highly unusual choice, right? Because most standardized cryptography used curves defined by NIST, like Sec256R1.
It was very unusual.
The R in that NIST curve stands for random, right? Like the parameters of the equation were generated from seemingly random seeds provided by the U.S. government.
Correct. And that raised a lot of suspicions among cryptographers.
I bet.
Because if you choose the starting parameters of a curve carefully enough, you could theoretically build a mathematical backdoor that makes the discrete logarithm problem solvable for the entity that generated the parameters.
So the NSA could just read everyone's data.
That was the fear. So Satoshi intentionally avoided the NIST curves and chose SecP256K1 because it is a Koblitz curve. The K stands for Koblitz.
Okay.
Its parameters are derived mathematically in a predictable way, leaving literally no room for a hidden backdoor.
Which is that nothing up my sleeve appeal.
Exactly. It was a paranoid choice that proved incredibly prescient, especially in a post-Snowden world.
For sure. And Ethereum ended up adopting that exact same SecP256K1 curve.
They did, yeah.
But the curve itself is just the mathematical landscape. To actually authorize a transaction, we use a signature algorithm built on top of it. For SecP256K1, that algorithm is ECDSA, the elliptic curve digital signature algorithm. And ECDSA has this brutal Achilles heel that has led to some of the most spectacular security failures in tech history.
Oh man, ECDSA is notoriously fragile when it comes to implementation.
How so?
To generate a signature, the math requires you to introduce a random ephemeral number called a nonce. It's usually denoted as a lowercase k in the equations.
Okay.
This nonce blinds your private key during the mathematical operation.
Wait, let me map the algebra on that. If the signature algorithm uses a random variable, k, to blind the private key during the assigning process, the math only remains secure if k is perfectly random and uniquely secret every single time you sign.
Exactly.
So if a piece of software reuses the same k for two different signatures, the two resulting equations now share a blinding variable.
And that is precisely the vulnerability. If an attacker sees two different messages signed with the same nonce by the same public key, it ceases to be a cryptographic challenge.
What does it become?
It becomes basic high school algebra. You have a system of two equations with two variables. You subtract one from the other, the blinding factor cancels out, and you can isolate and extract the user's private key instantly.
Instantly. That's terrifying. And this isn't just a theoretical math quirk, right? This exact flaw was responsible for the infamous Sony PlayStation 3 master key hack in 2010.
Yes, it's the textbook example of a catastrophic ECDSA failure.
Walk us through what happened there.
So, Sony implemented ECDSA to cryptographically sign all legitimate software for the console. If the console verified the signature against Sony's public key, the game would boot.
Simple enough.
But the engineers who implemented the cryptography hard-coded the nonce.
No way.
Yes. Instead of generating a secure random number for every signature, they used a constant variable.
Oh, that's a massive mistake.
A group of hackers simply took two signed games, isolated the signature values, ran the algebra, and extracted Sony's master private key.
Wow.
They could then sign custom firmware, and the console's hardware mathematically validated it as official Sony software.
And we've seen this exact attack drain cryptocurrency wallets when the device's random number generator is flawed or predictable, right?
Yes, unfortunately. Modern ECDSA implementations combat this by using RFC 6979, which mandates that the nonce must be deterministically derived from a hash of the private key and the transaction data itself.
So it's not relying on an external random number generator at all.
Exactly. It removes the element of chance. But newer blockchains, like Solana and Cardano, have bypassed the problem entirely by moving away from SEC 256K1 and adopting the ED 25559 curve, which utilizes the EDSA signature scheme.
Right, because EDSA is deterministic by design.
Exactly. It mandates deterministic nonces at the protocol level. It is also mathematically faster to verify and significantly more resilient against side-channel attacks.
Side-channel attacks.
Yeah, where an attacker might try to extract the key by, monitoring the power consumption or electromagnetic radiation of the hardware wallet during the signing process.
That sounds like science fiction, but I know it's a real threat.
It definitely is.
Okay, before we move off keys entirely, we need to clarify a massive operational gotcha for users operating across chains.
Oh, the compatibility issue.
Yeah, Bitcoin and Ethereum both utilize the exact same SECI-May 256K1 curve. That means the mathematical derivation from a private key to a public key is identical. Like, if I have a private key, the resulting coordinate on the curve is the same whether I'm querying Bitcoin or Ethereum.
The underlying key pair is identical. A valid Bitcoin private key is a valid Ethereum private key.
Okay.
But the way those networks serialize transactions, format signatures, and derive human-readable addresses from the public key is completely incompatible.
Ah. So if you somehow force a transaction to send Bitcoin to the Ethereum address derived from the same private key,
The network protocols will not recognize the formats. The keys are mathematically sound, but the execution environments speak entirely different dialects. You can't just cross the streams like that.
that is a crucial distinction, which brings us precisely to the mechanics of digital signatures. We have our data hash, we have our public-private key pair.
Right.
How does the actual sign and verify sequence execute when I hit send on a transaction? Like, what is really happening?
Well, a robust digital signature must provide three simultaneous guarantees.
Okay.
First, authenticity. The signature could only have been created by the holder of the private key corresponding to the broadcasted public key.
Check.
Second, integrity. The transaction data has not been altered by even a single bit since the signature was applied.
Check.
And third, non-repudiation. The sender cannot mathematically deny having authorized the transaction.
Okay, so what does the byte level workflow look like for the wallet software to guarantee all that?
Step one is serialization. The wallet takes all the parameters of your transaction, the recipient, the amount, the network fee, the nonce indicating transaction order, and packs them into a rigidly defined canonical byte string.
Okay.
Step two, it hashes that byte string down to a 256-bit digest.
Wait, it hashes it. It doesn't sign the raw transaction data.
No, asymmetric math is computationally heavy. Signing a massive byte string would take significantly more processing power.
Oh, I see.
By hashing it first, the wallet ensures it is always signing a fixed 256-bit payload, regardless of how complex the underlying transaction or smart contract interaction is.
That's super efficient.
It is. So step three, the wallet feeds that hash and your private key into the ECDSA algorithm.
And the output of that algorithm is the signature itself, which for ECDSA consists of two specific numerical values, right? R and S.
Correct. You broadcast the original transaction data, the R and S signature values, and your public key to the network.
And then what?
Every node that receives this bundle performs the verification step. The node independently hashes the raw transaction data you provided. It then feeds that hash your signature values and your public key into the verification algorithm.
And what does that output?
The math yields a simple binary outcome, true or false. No central authority is consulted. If it returns true, the node adds it to the mempool. If it returns false, it drops it immediately.
Just totally ruthless math.
Very ruthless.
Now, Ethereum executes a brilliant architectural optimization during this verification phase, though. We mentioned R and S, but Ethereum's signatures append a third value, a single byte known as V, the recovery identifier.
Oh, yes.
Why do we need V?
It dives back into the geometry of the elliptic curve. The value R in the signature is actually the x-coordinate of a point on the curve.
Okay.
But because the curve is symmetric across the x-axis, every valid x-coordinate corresponds to two possible y-coordinates, one positive, one negative, in the modular field.
So if a node only has R and S, there is an ambiguity about which point on the curve was actually used to sign?
Exactly. They wouldn't know which y-coordinate to use. The v value simply acts as a flag, telling the verification math which of the two y-coordinates to use.
So it just points them in the right direction.
Right. And by having R, S, and V, Ethereum leverages an operation called public key recovery, often seen in smart contracts as the eCover function.
Okay, I've heard of that.
Yet, given the message hash and the full signature, the math can be worked strictly backward to deduce the exact public key that must have produced the signature.
Wait, if the network can mathematically recover the public key from the signature itself, does the sender even need to include their public key in the transaction data?
They do not.
Really?
Really. If you look at the raw hex data of a broadcasted Ethereum transaction, there is no sender field. There is no explicit from address.
That's crazy.
The transaction only contains the recipient, the value, the data, and the signature. When a node processes the transaction, it runs the recovery math, extracts the public key from the signature, derives the Ethereum address from that public key, and dynamically assigns that derived address as the sender.
That is an incredibly elegant way to compress data at the protocol level. Like, it saves bytes on every single transaction.
It does. And the eCover primitive is deeply ingrained in decentralized finance. It's the mechanism that allows for gasless transactions or meta-transactions.
How does that work?
You can sign an authorization message off-chain, hand that signature to a relayer, and the relayer submits it to the smart contract, paying the gas on your behalf. The smart contract runs eCover on your signature, verifies it maps to your address, and executes the logic.
That's super cool. Now, you mentioned deriving the Ethereum address from the public key. This is a vital layer of abstraction, right?
It is, yeah.
Because public keys are massive, unformatted hexadecimal strings. Forcing humans to copy-paste 64-character raw cryptographic coordinates to send a payment is just a massive UX failure waiting to happen.
Oh, it would be a disaster. People would lose money constantly.
Right. So networks derive human-friendly handles addresses from these keys.
Exactly. An address is essentially a truncated, heavily encoded representation of the public key designed for human interaction.
Okay, let's look at Ethereum's derivation first, as it is relatively straightforward.
So Ethereum takes the uncompressed public key and hashes it using the Keccak 256 algorithm. It then takes that 256-bit hash, completely discards the first 12 bytes, and keeps only the last 20 bytes.
It just slices off the front of the hash.
Just chops it off. Those remaining 20 bytes, represented as 40 hexadecimal characters and prefixed with 0x, constitute a raw Ethereum address.
Okay, but raw hexadecimal is mathematically case-insensitive. Like, a wallet parsing 0 ABC evaluates it identically to 0's ABC in all caps.
Right.
Which introduces a critical danger, doesn't it?
Yeah.
If there's no distinction in the formatting, there's no internal mechanism to detect if a user accidentally deletes or modifies a character while copy-pasting. The funds would just burn into an inaccessible address.
That was a huge problem early on. To solve this without breaking backward compatibility with older wallets, the Ethereum ecosystem adopted EIP55.
Okay, what did EIP55 do?
It introduced a really clever checksum mechanism disguised as capitalization.
Wait, how does capitalization act as a cryptographic checksum?
It's an ingenious hack. A compatible wallet takes the lowercase version of your raw address, dropping the 0x, and runs it through Keccak 256 again. It then looks at the binary representation of that resulting hash. For every alphabetical character in your address, a throughfold on the wallet checks the corresponding index nibble in the hash.
And nibble being half a byte, right?
Exactly. If the value of that nibble is 8 or greater, meaning the leading binary bit is a lay, the wallet forces that character in your address to uppercase. If it's less than 8, it stays lowercase.
So the mix of upper and lowercase letters in an Ethereum address isn't just random styling. It is mathematically dictated by the hash of the address itself.
Exactly. When you paste that mixed case address into a modern wallet, the wallet reruns the Kekkak hash. It checks if the capitalization perfectly aligns with the resulting binary hash.
And if you mistyped a single character?
The avalanche effect of the hash function guarantees the resulting binary string will be completely randomized, the capitalization check will fail immediately, and the wallet will block the transaction.
That is brilliant backward compatibility. Because older systems that don't support EIP55 simply ignore the casing and process it normally, since the underlying 20 bytes remain unchanged.
Exactly. Pure genius.
Now, Bitcoin's address architecture takes a much more aggressive approach to encoding, and it's evolved significantly over the years.
Yes, Bitcoin has gone through a few iterations.
Like the legacy address is the one starting with you use a process known as #ASH160.
Right. Bitcoin takes the public key and hashes it with SHA-256. But instead of just truncating it like Ethereum, Bitcoin takes that output and immediately hashes it again using a completely different algorithm, RPMD160.
Okay.
This compresses it down to 160 bits, or 20 bytes.
And then it runs it through an encoding format specifically designed to prevent human optical errors, right?
Yes, base 58 check. Standard base 64 encoding utilizes all alphanumeric characters, including upper and lower case, plus some symbols.
Right, which can be confusing to read.
Exactly. Base 58 strips out the symbols, but more importantly, it deliberately removes visually ambiguous characters. The number 0, the capital letter O, the capital letter I, and the lowercase letter L are entirely excluded from the alphabet.
So if you print a Bitcoin address on a physical paper wallet, you never have to squint and wonder if a character is a 0 or an O.
Right. The check portion of base 58 check involves taking the HHH160 output, double hashing it with SHA-256, taking the first 4 bytes of that final hash, and appending it to the end of the address before the base 58 encoding.
Oh, I see.
That 4-byte checksum guarantees that if you type a character wrong, the hash fails and the wallet throws an error.
But the modern Bitcoin standard has shifted to BEC32, which are the addresses you see starting with BC1.
Yes, BEC32 was introduced with the SegWit upgrade to improve efficiency. It utilizes an entirely lowercase alphabet, making it much easier to read aloud or type without toggling shift keys.
Which is a nice quality of life upgrade.
It is, but the real upgrade is the error detection. Instead of a simple hash checksum, BEC32 utilizes a Bose-Chaudhuri-Hockenham, or BCH, error correcting code.
A BCH code, so it relies on polynomial mathematics rather than hashing.
Correct. The BCH code is so mathematically robust that a wallet doesn't just know the address is invalid. In many instances, it can mathematically pinpoint exactly which character you mistyped and auto-suggest the correction.
Wow, that's next level.
Furthermore, BEX32 maps flawlessly to the alphanumeric mode of QR codes, making them much denser and easier for cameras to scan quickly.
Okay, I have to pause here because there is a lethal assumption users make regarding these checksums.
Uh-oh. Yeah, I know where you're going with this.
Let's say a user's computer is infected with clipboard hijacking malware. The user copies their friend's valid checksummed address, but when they hit paste in their wallet, the malware silently swaps the clipboard data and pastes an address owned by the hacker.
Right.
If the user relies on the checksum to protect them,
They will lose everything.
because it's not verifying the person.
Exactly. This is a critical misunderstanding of what a checksum actually provides. A checksum, whether it's EIP55 or BEC32, only validates formatting.
Formatting.
Yes. It ensures the string conforms to the mathematical rules of an address and contains no typos. It provides absolutely zero identity verification.
So the wallet checks the math, sees a perfectly valid checksum for the hacker's address, assumes it's what you intended, and just fires the transaction.
Exactly. The protocol cannot know who owns the private key associated with that address. If malware pastes a validly formatted address, the transaction will succeed.
Which is why hardware wallets require you to physically verify the address on the device's screen.
Yes, an environment isolated from the potentially compromised operating system of your computer.
Correct.
Always verify on the device before signing.
Good advice. Okay, so we have established a robust framework for individual transactions. We have secure hashes, unforgeable signatures, and formatted addresses.
We have the building blocks.
But a blockchain processes millions of these interactions. If the integrity of the chain requires every node to verify every transaction, how do we scale this without requiring every user on a smartphone to download a terabyte-sized ledger?
Yeah, that would be impossible. And this brings us to a data structure invented by cryptographer Ralph Merkle in 1979, the Merkle tree.
The famous Merkle tree.
A Merkle tree allows us to take a practically infinite data set, compress its cryptographic proof down to a single 32-byte hash, and efficiently verify the presence of any specific piece of data within that set without needing access to the rest of the data.
So how does the network construct this tree at the block level? Let's walk through the architecture.
Sure, a Merkle tree is built from the bottom up, utilizing a binary tree structure. Let's assume a block contained exactly 1,000 transactions.
Okay, 1,000 transactions.
The protocol first hashes each individual transaction using SHA-256. These 1,000 hashes form the base layer of the tree, known as the leaves.
So we have 1,000 distinct 256-bit fingerprints at the bottom.
Next, the protocol groups those leaves into pairs. Hash 1 and hash 2 are concatenated together into a single string. That combined string is then hashed again to produce a single parent hash. Let's call it hash 1, 2.
Okay, simple enough.
Hash 3 and hash 4 are concatenated and hashed to produce hash 3, 4, and so on.
Got it. So by pairing them up and hashing them, the next layer of the tree is exactly half the size. We go from 1,000 leaves to 500 parent hashes.
Precisely. And this recursive process just continues. The 500 hashes pair up to become 250, then 125, continuing upward until only a single isolated hash remains at the apex of the tree.
And that final 32-byte hash is the Merkle root?
Yes.
And because of the avalanche effect we discussed back in Section 1, this singular root is cryptographically bound to every single byte of data below it.
It is. If you alter one byte in transaction 842, the leaf hash for 842 changes completely.
Right.
When that altered leaf is concatenated with its neighbor, their parent hash changes completely.
Oh.
The cryptographic fracture cascades upward through every layer of the tree until the Merkle root itself is completely altered.
So the root acts as an absolute tamper-evident seal for the entire block of transactions.
Exactly.
But the brilliance of this architecture isn't just the final root, though, is it? It's how the tree allows for logarithmic verification proofs.
Yes. The proofs are where the magic happens.
Like, I think of it as a table of contents fingerprint for a massive book. To prove page 547 has a specific paragraph, I don't mail you the whole book. I send the paragraph and a short chain of section fingerprints that lead back to the cover fingerprint we both already trust.
That's a great way to put it. This is the Merkle inclusion proof. If you want to prove transaction 3 is in the tree, you provide the raw transaction data. The verifier hashes it to find leaf 3.
Okay.
Then, instead of providing the other 999 transactions, you simply provide leaf 4 its sibling.
Right.
The verifier concatenates 3 and 4 to compute parent hash 3, 4. Then you provide the sibling to that parent, hash 1, 2.
So the verifier just keeps computing the hashes upward, combining their calculated results with the sibling hashes provided in the proof.
Exactly. They run the math up the branches until they calculate a final root. If their independently calculated root perfectly matches the Merkle root publicly stored in the block header, the math mathematically guarantees that transaction 3 was part of the original dataset.
And the scaling efficiency here is staggering. Because it's a binary tree, the number of hashes required for a proof scales logarithmically, not linearly.
It's exponential compression. If a block has 1,000 transactions, a proof requires about 10 sibling hashes.
Right.
If a block has 1 million transactions, a proof only requires 20 hashes. You can cryptographically prove the exact state of a single transaction out of a million by downloading near kilobytes of data instead of gigabytes.
And this logarithmic scaling is the entire basis for Satoshi Nakamoto's SPV simplified payment verification outlined in Section 8 of the Bitcoin white paper.
Yes. SPV is what allows mobile wallets to exist.
Because phones can't hold a 500-gigabyte ledger.
Exactly. A light client on your phone does not download the actual transactions of the blockchain. It only syncs the block headers, which are a fixed 80 bytes each and contain the Merkle root.
Okay.
When the wallet needs to know if a payment arrived, it queries a full node for the Merkle proof of that specific transaction. The node provides the short array of sibling hashes.
And the phone runs the math.
Yes. The phone runs the hashing math. If the computed root matches the header the phone already trusts, it mathematically verifies the payment without having to trust the node providing the data.
That is just phenomenal engineering. Now, Ethereum takes this concept even further with its state management, right? Because Bitcoin's Merkle trees are static. Once a block is mined, the tree never changes.
Right.
But Ethereum acts as a global computer. Account balances are constantly updating, smart contract variables are changing state. A static tree wouldn't work.
You're right, it wouldn't. So Ethereum utilizes a heavily modified structure called a Merkle-Patricia tree.
Trie, spelled T-R-R-I-E.
Yes. It combines the cryptographic guarantees of a Merkle tree with the dynamic routing of a Patricia radix tree.
So it's updatable.
Exactly. Instead of just proving a transaction was included in a block, the
Uh,
MPT allows Ethereum to maintain a continuously updating, cryptographically verifiable database of the entire global state. A light client can request a proof of a specific smart contract's internal variable, and the trie structure allows a node to provide a logarithmic proof that resolves against the state root embedded in the latest block header.
And we see this architecture deployed everywhere in modern crypto. Token airdrops are a perfect example.
Oh, perfect example, yeah.
Like, if a protocol wants to distribute tokens to 2 million eligible users, they don't loop through 2 million addresses and pay gas for each transfer.
No, that would bankrupt the protocol in transaction fees immediately.
Right. So what do?
Instead, they compute a Merkle tree containing the balances of all 2 million users off-chain. They publish the single 32-byte Merkle root into the claimed smart contract.
Okay.
When a user wants their tokens, they generate a Merkle proofs locally on their machine and submit it to the contract. The contract hashes the proof against the root. If it matches, it mints the tokens. It offloads the computational burden entirely onto the cryptography.
Man, math really has replaced the server here.
Complete.
So we've mapped out the entire mathematical landscape. We have the cryptographic fingerprinting, the asymmetric identity layers, the unforgeable signatures, and the logarithmic scaling structures.
We've covered a lot.
But all of this multi-trillion-dollar infrastructure bottlenecks at a single hypercritical point, the generation of the 256-bit private key.
The master key.
Right. And we noted earlier that humans are fundamentally incapable of interacting with raw 256-bit entropy.
Humans are deterministic machines governed by psychology and habit. We cannot generate true randomness. If you ask a human to pick a random string of characters, they will inevitably rely on patterns, dates, names, keyboard walks, or cultural references.
Which introduces the fatal flaw of the brain wallet.
Oh, brain wallets. In the early days of Bitcoin, users thought they were being clever by running a favorite quote or a line from a book through a SHA-256 hash function to generate their private key.
They assumed that because a quote was long, it was secure.
Right. The logic being, no one will guess this exact obscure stanza from this specific 18th century poem.
But they were wrong.
Very wrong. Because cryptographic security doesn't care about human obscurity. It relies on computational entropy. Automated bot networks continuously scan the blockchain, pre-computing the SHA-256 hashes of every sentence of every book ever digitized.
Oh, wow.
Every song lyric, every dictionary word combination, every leaked password database. They generate the corresponding public keys and monitor the chain.
And if someone uses one?
If a user funds an address derived from low entropy, the bot's script immediately drains it in the same block. It's gone.
That is ruthless. So a secure private key must be generated by a cryptographically secure pseudo-random number generator, a CSPRNG, that leverages physical entropy like thermal noise or atmospheric data to guarantee true unpredictability.
Exactly. The machine has to do it.
So the machine hands us a pristine, perfectly random 256-bit string, but backing up a raw hexadecimal string on a piece of paper is incredibly error-prone. One illegible character and the funds are lost. So to bridge the gap between high-entropy machine data and human usability, the industry standardized around BIP 39, which introduced the mnemonic seed phrase.
BIP 39 is an absolute masterpiece of UX engineering.
How does it work?
It takes raw binary entropy and maps it to a sequence of common, easily transcribable English words. Let's look at the mechanics of a standard 12-word seed phrase. The wallet first generates 128 bits of pure random entropy.
Okay, 128 bits of ones and zeros.
To ensure the phrase can validate itself against typos, the wallet computes a checksum. It hashes the 128 bits using SHA-256, extracts the first 4 bits of that hash, and appends them to the end of the entropy.
So now we have exactly 132 bits.
Yes.
But 132 isn't a random number, right? It's perfectly divisible by 11.
Precisely. The wallet slices that 132-bit string into 12 distinct chunks of 11 bits each. In binary mathematics, an 11-bit sequence can represent exactly 2,048 different values, ranging from 0 to 2,047.
The BIP 39 standard includes a rigidly defined alphabetical dictionary of exactly 2,048 distinct English words.
Yes. Each 11-bit chunk acts as an index integer pointing to a specific word in that dictionary.
So cool.
The first 11 bits might correspond to the number 42, which maps to the word apple. The next chunk maps to the word zebra. The wallet iterates through the chunks, translating the binary sequence into a 12-word phrase.
But the inclusion of the checksum fundamentally alters the nature of the final word in the phrase, though, right? Like, the first 11 words are derived purely from the random entropy. But that 12th word contains the checksum bits.
This is a critical mathematical distinction. You cannot simply select 12 random words from the BIP 39 dictionary and expect a wallet to accept them.
Because it won't balance.
Exactly, because the final bits of the 12th word are a cryptographic hash of the preceding entropy. The 12th word acts as mathematical lock.
Wow.
If you write your words down out of order, or substitute a word, the reconstructed entropy will produce a different hash. The checksum bits will fail to align with the final word, and the wallet interface will instantly flag the phrase as invalid.
So we have a human-readable backup. But how does the wallet translate those 12 words back into the cryptographic keys necessary to sign transactions?
The mnemonic phrase is fed into a key stretching function called PBKDF2. It runs the phrase through the HMAC SHA-512 algorithm exactly 2,048 times.
Why loop it 2,000 times? That seems computationally inefficient.
It is deliberately inefficient. The stretching function introduces artificial computational delay.
To slow down attackers.
Yes, if an attacker recovers a partial phrase and attempts to brute force the missing words, the 2048 hashing iterations severely limit the number of guesses they can make per second.
Oh, that makes sense.
The final output of this PBKDF2 function is a massive 512-bit string known as the master seed.
The specification also allows a user to introduce an optional passphrase during this PBKDF2 stretching phase, right? Often colloquially referred to as the 25th word.
Right, the 25th word. The passphrase acts as cryptographic salt. Because of the avalanche effect, adding even a single character to the passphrase completely scrambles the output of the stretching function, resulting in a fundamentally different 512-bit master seed.
So it creates a totally hidden wallet.
Exactly. This provides a mechanism for plausible deniability. A user can maintain a small amount of funds on the seed derived without a passphrase, while securing the majority of their wealth on a seed derived with a complex passphrase.
And if they're forced to hand it over?
If physically coerced, they reveal the 12 words, but the attacker only gains access to the decoy wallet.
But the danger of the passphrase is that it is not mathematically bound to the checksum, right? The wallet cannot tell you if you've typed your passphrase incorrectly.
That is the trade-off. If you forget your passphrase or remember capitalization, the wallet will silently derive a completely different empty universe of keys.
And there's no error message.
None. The funds on the intended passphrase are mathematically unreachable.
Scary stuff. Okay, this brings us to the final piece of the architecture. We have our 512-bit master seed. But modern users don't interact with a single private key. They have a Bitcoin address, an Ethereum address, a Solana address, and multiple accounts within each network.
Right, it's a sprawling setup.
In the early days, you had to manually back up a new wallet file every time the software generated a new key pair.
Managing a disorganized cluster of standalone keys, known as a JB, or just a bunch of keys wallet, was a logistical nightmare.
JB, okay, I haven't heard that in a while.
Yeah. If your hard drive crashed and your backup was 2 weeks old, any keys generated in those 2 weeks were lost forever. This structural failure was solved by BIP 32, which introduced hierarchical deterministic or HD wallets.
Deterministic, meaning the entire sprawling structure of keys is derived predictably from that single master seed.
Yes, from the 512-bit master seed, the wallet splits the data. The first 256 bits become the master private key. The second 256 bits become something called the master chain code.
Why do we need a chain code? I mean, if we want to derive child keys, why not just hash the master private key with an index number? Like, hash the master key plus the number 1 to get the first account.
If you simply hashed the parent private key, you risk exposing mathematical relationships between the keys. The chain code acts as external localized entropy for the derivation function. It cryptographically separates the parent key from the child keys.
Okay, that makes sense.
To generate a child key, the wallet runs a one-way HMAC function that takes the parent's public key, the parent's chain code, and the requested index number. The output of that function is mathematically added to the parent's private key to produce the child private key.
So the software can generate a practically infinite tree of keys. A parent key derives child keys, which can derive grandchild keys.
Infinite branches.
And because the math is deterministic, you only ever need to back up the initial 12 words. The wallet simply recalculates the entire tree on the fly.
The architecture is brilliant, but standard derivation introduces a subtle vulnerability.
There's always a gotcha.
There is. The math allows for something called public child key derivation. This means a server can generate all your child public keys without ever needing your parent private key, which is great for auditing.
Sure.
But because of the algebraic properties of the derivation, if an attacker somehow compromises the extended public key of a parent and manages to steal the private key of just one child account,
Yeah.
they can run the math backward to calculate the parent's private key.
Wait. If one child private key leaks, it compromises the parent key, which compromises every other branch on the tree.
Under normal derivation, yes. To patch this, BIP 32 introduced hardened derivation.
Hardened derivation.
Hardened derivation alters the mathematical inputs. Instead of using the parent's public key to derive the child, it forces the use of the parent's private key.
Which severs the mathematical link.
Exactly. If a hardened child private key leaks, it is impossible to calculate upward to compromise the parent. The upper levels of a wallet's directory tree are always hardened to act as cryptographic firewalls.
Okay, so we have an infinite mathematically secure tree of keys. But if every wallet app uses the same BIP32 math, how does an interface know which branch contains your Bitcoin and which branch contains your Ethereum?
Without a standardized map, wallets would be blindly searching through trillions of possible derivation indexes forever. So BIP44 provides that global map.
Yep.
It defines a rigid directory structure for the derivation paths, written out much like a file path on a computer, typically looking something like M446000.
I think of the 12-word seed phrase like the master key to a hotel with infinitely many numbered rooms. BIP32 cuts the room keys from the master, and BIP44 agrees on the room numbering scheme, right? So any locksmith or wallet app finds your Ethereum in room 60 and Bitcoin in room 0.
That is a perfect analogy. Let's decode that path really quick.
Sure.
So the M represents the master seed. The 44 indicates that this path complies with the BIP44 specification. The apostrophe signifies that this level utilizes hardened derivation for security. The next integer is the registered coin type. Bitcoin is designated as 0. Ethereum is designated as 60. Solana is 501.
So the derivation path for Ethereum explicitly instructs the mathematical tree to branch down path 60.
Exactly. The next level dictates the account number, allowing users to silo their funds into multiple distinct accounts on the same network.
Like account 1, account 2.
Right. The subsequent level defines whether the derived address is for receiving funds or acting as an internal change address. And the final integer is the address index itself, address 0, address 1, address 2.
Because of this standardized architecture, a user can lose their hardware device, purchase a device from a completely different manufacturer, input their 12 words, and the new device immediately queries path 0 to find their Bitcoin and path 60 to find their Ethereum.
The interface simply follows the BIP44 map down the deterministic tree. It creates a perfectly interoperable standard across the entire decentralized ecosystem.
It's beautiful.
But it also enforces an absolute, uncompromising reality regarding custody. The 12 words are not a password to access an account. The 12 words are the cryptographic material. They're the root of the entire mathematical tree.
If an attacker gains access to those words, they possess the exact same cryptographic authority over the assets that you do.
Yes. There is no central server tracking IP addresses,
Yeah.
no fraud department to freeze the transaction, and no database administrator capable of reverting the state.
The cryptography operates exactly as it was mathematically designed to. It is the ultimate manifestation of self-sovereignty, but it demands an infrastructural level of operational security from the individual.
It is the raw distillation of the original cypherpunk ethos. We have constructed an architecture of trust built purely on cryptographic equations rather than human institutions.
So true.
We use hashes to provide unforgeable data fingerprints. We use asymmetric elliptic curves to establish identity. We use digital signatures to mathematically guarantee intent. We compress the data into logarithmic Merkle trees to achieve global scale. And we anchor it all to a deterministic master seed.
The sheer elegance of how these primitives interlock to form a functioning global economy is staggering once you see the byte-level mechanics. We started with data fingerprints, turned them into identities and authorizations, made them human-readable, scaled them, and packed them into a 12-word master key. Math has entirely replaced the trusted server.
It is mathematically beautiful. But,
Yeah.
to leave you with a final vector of analysis.
Oh, here we.
Every primitive we unpack today, from the hash functions to the elliptic curves, relies unconditionally on a computational impossibility of brute forcing a 256-bit space.
Right.
It assumes that calculating the discrete logarithm on an elliptic curve requires exponential time. However, the theoretical framework for quantum computing, specifically Shor's algorithm, threatens to collapse that exponential complexity into polynomial time.
Meaning a sufficiently advanced quantum computer wouldn't need to guess the keys. It could fundamentally solve the equation backward, deriving the private key directly from the public signature.
Precisely. It challenges the bedrock of the entire architecture.
Wow.
The cryptographic community is already intensely focused on post-quantum cryptography, engineering new primitives based on lattice cryptography or hash-based signatures that remain mathematically intractable even for quantum architectures.
But migrating everything.
The migration of trillions of dollars of value from elliptic curves to quantum-resistant structures will be one of the most complex logistical feats in the history of computer science.
And that impending upgrade is a deep dive for another day. Thank you for joining us on this exploration of the cryptography powering the decentralized world.